This is the lecture for Part B of Module 2 of Unit 4. This brief lecture introduces some qualitative thinking about equilibrium constants and LeChatelier's principle. Here is a reiteration of LeChatelier's principle, which we've discussed briefly before. If a stress is applied to a system at equilibrium, the composition of the system will change to counteract the applied stress. Alright, we've been thinking about equilibrium now in this unit. Consider a system at chemical equilibrium. Let's take acetic acid and water as just one example. If we think about LeChatelier's principle, we should be able to determine the effect of adding reactant to the mixture of acetic acid and water. In other words, what happens if we add more acetic acid? Or of adding product, which might be adding acetate ion, for example. Or adding a strong acid to increase the acid concentration. Alright, here is an illustration of LeChatelier's principle using the acetic acid equilibrium. The reaction, you know, is acetic acid reacts to make H plus and acetate ions. Both the forward and backward reactions are happening at equilibrium. At equilibrium, K is a number which is equal to the reaction quotient, which is the ratio of product concentrations over reactant concentration. All right. Now, let's think about the effect of adding reactant on the reaction quotient. If the concentration of acetic acid goes up, Q, the reaction quotient, becomes smaller. Q will become larger again and become equal to K if the reaction proceeds to the right, if the balance shifts so that more acetic acid reacts to make more product. So the system, according to LeChatelier's principle, or I should say the system will obey LeChatelier's principle and will shift to more product to restore equilibrium. Likewise, if we add H plus or acetate to increase the concentration of product, Q is now too large. Q can become smaller or become smaller as the balance for this reaction shifts to the left. More product reacts to make more reactant. And this shift to the left side will continue until Q has become equal to K again. So in any equilibrium, you can anticipate making the reaction go to the right by adding reactant, or go to the left by adding product. Likewise, if you remove reactant, you can also make a reaction go to the right. Other effects to consider besides changes in concentration and how they will affect Q is the effect of temperature. For example, an exothermic reaction makes heat as it occurs. It will shift to the left toward the reactants if the temperature of the system is increased, i.e. if heat is added. An endothermic reaction, which needs heat to occur, will shift to the right toward the products if more heat is supplied, if the temperature of the system is increased. If a reaction has a delta H of 0, then a change in temperature will not affect the equilibrium composition. Changes in volume and pressure may affect equilibrium, in particular if there are gases involved. Solids and liquids are not very compressible. They have very little responsive volume if pressure is changed. On the other hand, you know the gases do experience volume changes if pressure is changed. So, increasing the pressure on a system or decreasing the volume will favor the side of the reaction that has fewer gaseous molecules. Consider this reaction, for example, in which 2 moles of SO2 gas and a mole of O2 gas react to make 2 moles of SO3. There are 3 moles of gas on the left, 2 moles of the right. Decreasing the volume or increasing the pressure will favor the right-hand side, the one with fewer gaseous molecules. So an increase in pressure produces more product in this case. This concludes this brief qualitative review and how changes in concentration, temperature, or pressure will affect the balance in reactions at equilibrium.